So we would like actually to switch the gear to a new things which we will cover deeply, which is basically the memory. But just like as a reminder that under the computer, we have the processor, control, data path, and so on and so forth. And these things we already covered in details. We have seen like how the data will enter from the very beginning all the way till the end until we go to the memory or vice versa and stuff like that. But we didn't go deeply inside the memory, which we will do in that particular time or that particular chapter. We'll go deep inside the memory. We'll understand how we deeply interact with the memory. What are the type of memories that we will deal with, how they are interacting with each other, and all of these kind of stuff. So we have the hard disk, what we call secondary memory. We have the main memory DRAM, and we'll introduce what is exactly DRAM means shortly. And we have the cache memory, SRAM, and we will introduce also shortly what is SRAM is. Also, we will in the next chapter, we will introduce the input outputs, how we interact with the inputs, outputs, and stuff like that. That would be covered a bit later. So again, in the memory size, we have the hierarchy, the disk. This disk can be magnetic or it can be flash. The main memory. But also inside the cache, we might have levels inside my hierarchy. I can have even levels. I can have level 1, level 2, level 3. We'll understand these levels and why you would have these kind of levels and so on and so forth. We'll go deeply on all of these explanations. So just to highlight that the cache memory is using the SRAM. S is referred to static random access memory. Static random access memory, or SRAM. The good thing about this SRAM that actually the access time is 0.5 to 2.5 nanoseconds. As you can see, nanoseconds is very, very fast. But the problem or the drawback of such component or of such SRAM is its low density. The size is very small. High power, it consumes high power. And also it is expensive, unfortunately. So you are getting one things from the side and you actually are losing other things from the other side. The trade-off. But you need that fast access time. But unfortunately, you are losing other stuff. On the other hand, the DRAM, which refers to the dynamic RAM, random access memory, has higher density than the SRAM, has lower power than the SRAM. It's also cheaper than the SRAM, but the drawback, again, here the access time, 50 to 70. Can you see? This is 0.5, this is 50. So that means that approximately 100 times slower than the SRAM. Huge amount. Yes, it is much bigger, it is cheaper, lower power, but you are losing other stuff on the other hand. Also with the dynamic, because it is dynamic, so it needs to be refreshed regularly, approximately every 8 milliseconds, which means that I am also consuming more from my time, 1 to 2% of the active cycles, which will make it even more slower, because each approximately 8 milliseconds, I need to refresh that, which is eating also from that time. There is also a secondary memory, for example, a non-volatile hard disk. It's extremely high density, very cheap, but again, the access time, unfortunately, is very slow comparable to the DRAM and, of course, the SRAM in this situation. It's much slower, lower cost, and of course, it's not volatile. This is used in the magnetic disk. The flash memory can be substitute the magnetic disk. It's currently used, something intermediate between the DRAM and the magnetic disk. However, still there is some limitation on the size of that and also the price. It's not as cheap as the magnetic disk, and it's not as large as the DRAM. So how actually to exploit all of these things? We need to get a fast access time, lower power, cheaper stuff, and a high density or high size. The idea came to researchers that we need to actually exploit what we call the hierarchy scheme. That we will try to get actually the fast access time also with the other things. So we can have at the very end all of these kind of stuff together. So I can have either cheap or expensive per bit, slow or fast access time, large or small quantities of bytes, and so on and so forth, as we will explain in details shortly. Just for your reference, that on a chip, examples for on a chip is the SRAM and the embedded DRAM. Examples for off a chip is the DRAM, flash, magnetic disk, and all of these kind of things. Also for the removable, it can be flash, magnetic disk, or optical disks. It can be also have this as a network, which can be a file server or web server or stuff like that. But our concentration actually will be on the side of the the memory, the DRAM, and the SRAM in this particular case. But with this hierarchy scheme, how I can act or exploit this kind of stuff? They mentioned that try the fast parts first. So this will be the first idea. Second idea, move stuff that is using most of the time, and this will work well with the closest to the processor, as we will explain. Then try to do this kind of things as much as possible so you can have actually at the very end a better performance. This is with hierarchy. Another path that you can try is to do the parallelism, meaning that you will use multiple identical parts, either in the operating system or the hardware or whatever the stuff, in order to exploit the parallelism. However, we will concentrate more in that scheme, which is the hierarchy. So here is exactly what is meant by hierarchy. So you have the processor here. And what is mentioned in that hierarchy is that please allocate close to the processor the memory that is fast with lower size. And while you are going away from the processor, the memory size will increase, but unfortunately, the access time also will increase, meaning that this will be very fast transferring the data from its location to the processor, but unfortunately, I do have a very low amount of data. With this one, I have a higher amount of data, but the access time will be a bit higher. The same here and the same here, and so on and so forth. So here is very large data, but the access time, unfortunately, is very slow in this particular case. So as the furthest from the processor, the highest access time, and also the larger size in that particular case. So this is what we meant that try to put closer to the processor the memory that actually have a fast access time. But we have also mentioned that try to move stuff that is accessed more frequently to the fast access time memory. How we can do that? Here is a nice principle called principle of locality. There is temporal locality and there is spatial locality. Let's introduce each one of them so you can understand what is meant by these two expressions. Temporal locality means that items accessed recently are likely to be accessed again. So please keep the most recently accessed data items closer to the processor. We didn't understand what does that mean. That means that if you are using something very frequently, since you are moving very frequently, so try to move it to the stuff that actually the access time is very, very slow. So that's what it meant by quick, yes? Sorry, not very slow, very low. Very low. The access time will be very low, so it will be quicker. Is that enough? If this will help the throughput? Yes, it will help the throughput. If there is any other idea, Yes, there is another idea that's called the spatial locality. Spatial locality, items near those accessed recently are likely to be accessed. So please also move it closer. That means that if you are using a certain particular data frequently, anything that is close to this data, also move it closer, because there might be high probability of accessing these things soon. Oh, yeah, you introduced that, but we still did not understand deeply the meanings of whatever you are mentioning. Okay, that's fine. So let's introduce that from the real life situation. And you will find that the idea here is exactly the same as we are thinking in our real life. Suppose that you have an exam of a certain class tomorrow, and you are studying for that class for today to study for tomorrow's class. If I am visiting you and you are at your desk, what I'm expecting that you will have at your desk? Of course, what you will bring to your desk in your room, all of the stuff that belongs to that particular exam, correct? You will see like whatever, maybe the textbook, you will take whatever the computer that has all the labs, you might have printed some of the review questions, or you have tried it or stuff like that. All of these kind of things that is used or be useful for you for the following day's exam, it will be on your desk. And you have to think with the same things, actually, that access time. You don't want each time you need something that you will go away from your desk to another place and return it back. Yes, you would like all of the stuff to have a very quick access time. You would like all of the stuff to be at your desk. And this means that the frequently used stuff will be closer to you. So you are the processor, the disk is the cache memory, and you are putting all of the things that you are using frequently and recently closer to you. Same idea. Exactly. How about the exam that is the following days, or maybe like 2 days or 3 days away from you? It will not, of course, that close as that particular class, but it might be still not that far. So it might be in another storage in the room, or maybe if you leave that room in an apartment, that storage will be in the apartment and so on. So it's not that far, still close, but it's not as close as the one that is very frequently used. This is what we call temporal locality. I am exploit temporal locality mechanism. I am getting all of the stuff that is frequently used and needed recently close to me. Because if I didn't do that, unfortunately, my performance will be affected badly because of the access time. Why? Suppose that you forgot to have close to you the review questions with the solution. Then, if you didn't find on the desk, you have to stay away from the desk and try to search for these couple of things. This means that you are consuming more time. The throughput or the performance will be decreased, correct? If you would like to finish these type of things in 1 hour, now we need actually more than 1 hour, because you have spent more time just searching for the materials that is needed frequently, and it's not available to you. Oh, so now we understand the temporal locality. What is the spatial locality then? From the real life situation also, suppose with the same example that you have an exam for a certain class tomorrow, and you went to the library to bring the textbook that belongs to that class. When you went to the library and you are just try to hold away or take away or borrow the text for that particular class, your eyes saw that there are other books close to that book that has this approximately similar content or approximately similar titles. If you are keen that you get a higher grade or a better grade in that particular class, you might say to yourself, why not to bring with me also other textbooks that has the same titles in case that I am studying from that particular textbook and I didn't understand. So why not to have another references in case I didn't understand and I don't have to lose time to go back again to my library. So I put all of this onto my desk, and that's a spatial locality. You are exploiting the spatial stuff that is close to whatever you would like to access frequently, just in case, because there is a high probability that you might need that as well. There is no guarantee, it's just a probability. There is no guarantee that you will open that textbook, but just in case. Because otherwise, if you didn't do that, anytime that you read the materials from that textbook and you didn't understand, you have to spend maybe 15, 20 minutes at least walking to the library back and forth in order to bring that textbook. So the access time or the whole performance decreased. And this is what we call by spatial locality. There is no forcing that you need to exploit both. It's like a designer decision. It's your decision as a student. You might say, I would like to exploit the temporal locality, that to bring everything on the disk. Maybe you said, no, I don't want that. Maybe you said, no, I would like to exploit the temporal locality and the spatial locality. It's just a design issue for you, yes? It's something that you decide. This is the idea, and it is there. If you would like to use it, try it. So basically, as I mentioned, you can take advantage of this locality. So the very first thing, you can have everything in the big storage unit, and then you can move from that big storage unit to these hierarchy steps as soon as needed. As an example, you have a big storage unit in the building, and then you have another smaller storage unit in the apartment, and then another smaller storage unit in the room, and then the very closest to you is your desk. You might begin to move things from the very far, which has a big space, to the closer one as needed. The good things about the hierarchy that actually part of the stuff that is in the, sorry, whatever you have in the cache or the closer level is part actually from whatever in the bigger memory and so on and so forth. It's just part of this, and part of the L2 cache. So the L2 cache will be part of the next level memory and so on and so forth. It's just moving from the one of this hierarchy level to the other one as needed. So you might copy recently accessed items from the disk to the smaller DRAM. So might copy stuff or just take stuff from the storage of the building to the storage of the apartment, just to be a little bit closer. You might also then do it another step. You might move things from the DRAM to the SRAM. You might move stuff from the storage of your room to a little bit more even closer to your disk, or from the apartment storage to your basically room storage and so on and so forth. So we need a little bit to introduce the implementation wise. Okay, so we did understand the idea, but then implementation, let's go step by step by how we can do that. And let's familiarize ourselves with some of the expression. So this is the processor. Let's assume that this is the first level memory. This is the second level memory and so on and so forth. Of course, if you are studying something, the very first place to search for is at your desk, correct? You are the processor. You would like to search for something, then you will search for on the desk. If you found it, that will be great because the access time is very fast. It's quicker. I don't need to go away from the desk. I can just use it. This would be the very good things. And this is what we call the hit, that you have already hit whatever you intended to. You found whatever you intended to. This is what we call the hit. Meaning that access satisfied by the upper level. Upper level here in this case, meaning the closer to you. And the closer to you is the disk. You found whatever you intended to use, and it is already on the disk. So this is hit. This means that you already hit whatever you are targeting. There is also a hit ratio, which is the number of hits per accesses. How many hits did you get upon all of the number that you are trying to access the data? For instance, you would like to access a certain type of things from your desk 10 times. 5 of the times you found the stuff, another 5 times you didn't find the stuff. So the hit ratio in this case would be 50%. How about the other 50%? The other 50% is basically what we refer to as miss ratio. Miss ratio means that you missed whatever you were looking for. You were looking for a certain particular text or a certain particular material for that class. You didn't find that on the desk, and that's why you miss. And accordingly, you have to pay more time to get the stuff from the library, or to get the stuff from the storage in the building, or from the stuff storage of the apartment, and so on and so forth. So there is miss penalty, something that you need to pay if you miss. So missing means that you didn't find whatever you are intended to in the upper level, and you copied this from the lower level. I brought it from the storage of the apartment to the desk. I paid some time, yes, either 15, 20 minutes, 5 minutes, whatever, but it is not on my desk. And accordingly, the miss ratio will be the number of misses divided by the accesses. And as you can see from the example that I mentioned, if this is 5 times you have been able to find whatever you're looking for, and the other 5 times you haven't been able to find what you're looking for on the desk, so it's 50% hit, 50% miss. So this means that if you had add the miss rate and the hit rate, it's equal to 1. Miss rate plus hit rate is equal to 1. 50% and 50% is just 100%, meaning that one is 1 minus the other. Also, the hit time is just time to access that particular level, which is time to access the block plus time to determine if it hits or miss. Of course, we expect that the hit time will be very low, yes, because it's a quick, yes, the hit time, it usually will be very low number, because it's just the time that you will access the stuff that is in your desk, and the time that you have decided or you found that, yes, it is here or not. Suppose that you are looking for a certain material that you would like to study. You need first to search for this material on the desk. Then you found it, so you will decide that you hit. Then you will begin to access. All of this is what we call the hit time. Miss penalty means that whatever you pay if you didn't find the material that you intended to use. And of course, in that sense, the miss penalty usually or always is greater than the hit time. Because now I have to move away from my desk all the way to the storage in the apartment or in the building, whatever, the needed material, and then I have to bring it back to my place. I have to bring it from that storage, move it to the desk, move it to the cache, move it to the upper level that is very close to me. If I have multiple cache, suppose that I will call anything in my room cache. I have a level 1 cache, which is the desk, level 2 cache, which is still inside my room, but it is not on the desk. So still very quick, but it's not as quick as the desk. And of course, it's not as small as the desk. It might be a little bit bigger, and so on and so forth. So that is the memory, for instance. And you would like to target something that is not here. Then what you need to do, that if it is not here, you need to go all the way till the main memory and copy it to the upper level, which is the cache. In this situation, this is the cache after I have already brought whatever I missed. I missed something, I went to access it, it's not there. Then I went all the way to the main memory, I copy it from there, I bring it to my cache memory, and it is now there, and then I can use it from now on.